So today we're going to be looking at the third way to find rate laws, which is a graphical it's the graphical method of integrated rate laws. Um, so starting off, I'm just going to give you a few relationships, a few equations, and then we will also look at that in relationship to what type of slope it's going to make and all of that. So first one we're going to look at is a zero order reaction. If you were to write a rate equation or a rate law for a zero order reaction, you would have this: rate equals K, K times concentration of A raised to the 0 power. Now, if we are to integrate this with time, the relationship that you get is concentration of A minus the concentration of the original concentration of A equals K times T. And I think that's actually a negative KT. Negative KT. All right. Now, if we linearize it, basically putting it in slope form, you're going to have concentration of A is equal to KT plus original concentration. And if you recognize this, this is Y equals mx plus b. That is your slope intercept. Yes, it is negative KT. Sorry. That is a slope intercept form. Now, so looking at it in the graph form, on our x-axis we're going to have time. On the y-axis you're going to have concentration, and your graph is going to look something like that, right? So the absolute value of m, the absolute value of your slope, is K. So if you ever need to find the rate constant and you know the slope, that is your K. I am going to skip half-life for just a minute. We'll come back and talk about that one. So go ahead and go down to the next one. So let's look at it for a first order reaction. So for a first order reaction, we get our rate law that basically rate is equal to K times concentration of A raised to the first power. And then if we integrate it with time, we're going to get this one ends up being the natural log of A minus natural log of original A equals negative KT. All right, putting it in slope-intercept formula, you're going to have ln concentration of A equals negative KT plus ln original A. All right, and again, you have your Y, you have your M, you have your X, and you have your B. So our X is still going to be T, but what is going to be our Y on this one? Anyone? Our Y is ln. All right. And again, the graph on this one is going to be a negative slope. So absolute value of the slope is equal to k. No. And then skip that half-life. We'll come back to that one. And then let's look at second order reactions. Second order reactions, again, the rate law is going to be rate equals K times concentration of A raised to the second power. So when we integrate this one with time, we end up with 1 over A minus 1 over original A equals KT. And this one is not negative KT. It is a, we only do 0 first and second. If there's more, I don't know because I've never done them either. All right, so on this one, just shifting it, you're going to have concentration of 1 over A equals KT plus 1 over A naught. So that means our X is time and our Y is 1 over concentration. And then again, so on this one, our slope, we have a positive slope. So K is equal to M. And the whole thing about the absolute value, you just can't have a negative K. So K is always going to be a positive number, so that's why we say it's the absolute value of the slope. All right, so let's go back to deriving the half-life equations. So a half-life for a first order, and for a zero order, I'm only going to do half-life for zero order and half-life for first order. I'm going to give you an actual equation. But before I move on to that, if you look down on the equation sheet that I gave you, I actually, on this equation sheet down at the bottom left-hand corner where it says kinetics, I actually gave you the equations for a first order and a second order reaction. And then you see that T1 half down at the bottom. That is the T1 half for a first order equation. And I'll show you how we get there. So you will have these equations on there. You're not going to have it for zero order, and you're not going to have the half-life for zero order or the half-life for second order. But we'll go ahead and look at this. So the first thing I need you to know, and let me come back to it right there. First thing I need you to know, when you hear the term half-life, what do you usually think about? Decay. Radioactive decay is what we usually come to. But a half-life is simply the time required for an initial concentration to fall to half of its original value. So, again, for a zero order, we have concentration of A minus concentration of A naught, which is your original concentration, equals negative KT. So, if I'm looking at this in terms of a half-life, I could say that the concentration of A, and this is just, let me write this in a different color so that we don't confuse what I'm doing here. I'm just going to establish another way that we can identify A. So concentration of A is equal to, in this case, since we're looking at a half-life, it's going to be half of the original. So A0 divided by 2. Y'all see how that works? So anytime I have concentration of A, I can substitute it with A over 2. So when I rewrite this to manipulate it for half-life, I'm going to say that concentration of A naught over 2 minus A naught equals negative K half-life. And the T half just means half-life. All right, so we can further manipulate this equation to where we get this final statement that T1 half half-life equals A naught over 2K. And getting from where we started to there is just algebra manipulation of the equation right here. I'm not going to go through all of that. I just want you to see. You do, unfortunately, have to memorize this one. But if you think about it, all you really have to remember is this, so you can plug in your original concentration, and then for A, you just divide your original concentration by 2, and you can solve for there. All right, and then going to the half-life for a first order, again, we start off with the same thing, Ln concentration of A minus Ln concentration of A naught equals negative KT. So if I substitute in A for half-life, I'm going to have Ln A naught over 2 minus Ln A naught and then going through further manipulation. I gave y'all the wrong one, I think. Nope, I didn't. So you end up when you manipulate it, you end up with Ln 1/2 equals negative KT half. So somebody tell me, what is the Ln of a half? What is natural log of half? Yeah. It's not that weird. That's not right. If you go, where's natural log? That is. Oh, I thought you said 0.169. So natural log of 1 divided by 2, we get a negative 0.693. I just heard you wrong. I'm sorry. So we get negative 0.693 equals negative KT 1/2. That, again, that T 1/2 is just telling us this half-life. All right. So we can further manipulate it, and if you look on your equation sheet, you should see this one on there. So half-life equals 0.693 over K. And that one is all the way down at the bottom. So that is your first order half-life. And the only other thing that I want to say about this is all radioactive reactions are first order. All radioactive reactions are first order. All right. So that basically gives us the equations that we're going to be using today for the most part. I'm not going to do a second order half-life, but if I were to set it up, if you look at second order, basically what you're going to write is it's going to be 1 over A naught over 2 minus 1 over A naught equals KT 1/2. So the only thing that I want to point out is that T1/2 just tells you that it's half-life. That does not mean that you take the time and half it. That's a symbol. That's not a unit or a conversion that needs you to do. All right. So if you flip over to the next page, you'll see that I have. No, that's not what I'm looking for. Yeah, it is. You should have a part that says Summary of Graphical Methods. Do y'all see that? All right. So where it says Summary of Graphical Methods, I'm just going to go ahead through this. This first one is for, this is for first order. Where's my second order? My zero order. Oh, it's down at the bottom. All right. Where it says Summary of Graphical Methods, this is our zero order. Above the zero order, go ahead and put C. And C tells us that our y-axis is concentration. For the second order one, for the first order, which is the next page, for that one, I want you to put a capital L above it, because L tells us that the y-axis is the natural log, or Ln, of concentration. And then the last one is a second order. And second order is going to be R, because, what did I say R was? Oh, because R, the y-axis, is the reciprocal. I think I misspelled reciprocal, but basically you get 1 over concentration of A, which is a reciprocal, right? 0 is C. So to remember them, it should be clear. So you get concentration, Ln, reciprocal. And that's just a little mnemonic thing. It's not anything other than that. All right. So go ahead, let's do a problem or two with these. Um, I don't think it's going to be necessary to work every one of these problems. It's just application of a formula, plugging in the numbers in the right place, but if we feel like we need to, we will. So reading the first one, it says the decomposition of H2O2 to water and oxygen follows first order kinetics with a rate constant, that's our K, of 0.0410 minutes, 1 over minutes, at a particular temperature. So we have the reaction of hydrogen peroxide splitting into water and oxygen, and it says calculate the H2O2 concentration after 10 minutes if our original concentration is 0.2 molar. So since this is first order, the first order reaction is the natural log negative KT. All right, so we're going to go ahead and plug in our information. We don't know the concentration of A, which I could actually replace this with. I could replace that with H2O2, but I'm just going to leave it as A for this part. And then we do know our original, so what am I going to put in here? So I'm going to put 2.200 molar equals our K, which is negative point. Yeah, sorry. Times the time, and they said after 10 minutes. Now, the thing to notice here is our time is in minutes and then our units for rate is in minutes. If the units for rate would have been 1 over seconds, you would have had to change your time into seconds. So just pay attention. They will do that in problems. All right, so looking at this, the way I approached this is I went ahead and solved this side first, and then I divided it by my ln. I added it to that. So I basically had ln of A is equal to 0.410 plus my ln of 0.200. So what do we get? What is ln of A? No, because 0.0410 times 10 is going to be 0.41. It's going to be a negative. So what number do you forgot to do the negative in your equation. You forgot this was negative. It should be negative 0.410. Can do it that way. The number I got, and see if you got it. Did anybody get negative 2.02? Oh, that's not what I want. I want this. I wish this was larger. Yes. Yes, you may. All right, so I got, I did negative 0.410 plus ln 0.2 If you leave that negative sign off, you get the 0.1, because I did that the first time too.
It's like if you change ln first, it's like a negative number.
But you're still adding it to a negative number plus a negative number.
Yeah, like you would change the sign.
Yeah. Yeah, I did it wrong the first time too, and that I kind of caught myself on it. All right, now the way that basically does anybody know how to change this just to get to concentration of A? How do we do that in the calculator? You basically it's second ln, which gives you that little e, and I can't see this far. So you're just basically going to go second ln, which gives you the e, and it's going to be to the negative 2.02, and then that gives you your number. So fairly straightforward. So we end up with 0.133, and it's going to be 0.133 molar since it is concentration. I wish I could make this thing bigger. All right, so does everybody see how we got there? All right, so let's look at number 10. Number 10 says the decomposition of N2O5 to O2 and NO2 follows first order kinetics. If a sample at 25 degrees with the initial concentration being 1.25 times 10 to the negative 3 molar falls to 1.02 times 10 to the negative 3, in 100 minutes, calculate the rate constant for the reaction. So again, it's first order, so we're using ln A minus ln A naught equals negative KT. And we're solving for K this time. So we're going to plug it in. ln A is going to be 1.02 times 10 to the negative 3 molar minus ln 1.25, because that's our original. I mean, I could, because I had information for both. This is my A naught, and this is my A. So I was given.
We're trying to find K.
I'm trying to find K this time.
So wait, how do you know when it's A and A naught?
Well, so your original concentration is always going to be larger, because it told us right here. It said initial concentration.
So that's always your bigger number?
Yeah. Or if it says the initial concentration, the other one's bigger, then it's going to mess up the equation, but it'll work still. Just always look for this initial or original concentration. All right, so it'd be K times 100 minutes, right? So now we're trying to solve for K, so go ahead and plug it in and tell me what you got. Because I don't think I finished it. Back there. I think I just plugged in the calculator wrong. All right. Moving forward. Next one says, in problem 9, how long would it take for half of the H2O2 to decompose? So I'm just going to go ahead and transfer some of the information. Our A naught concentration is equal to 0.200 molar, and our K was equal to 0.410, wasn't it? 0.0410. Now, so if we use our half-life equation for first order reaction, that's going to be this 0.693 over K. So all we really have to do is we don't even need the original concentration. We just need to plug in K. So half-life is equal to 0.693 divided by 0.0410. And so T half is equal to 16.9, and I believe it was minutes. All right, I'm going to skip 12. No, we're actually going to do 12. All right, so looking at number 12, know that number 12 is a second order reaction overall. Number 12 is a second order reaction. So in this one, and I'm not going to do it, I will just set it up. 1 over A minus 1 over A naught equals KT. All right. No, this one is not, because you've taken care of that with the reciprocal over here. So we have our K in this equation. We have our A naught right there, and then we have our time. So we're solving for A. So it's 1 over A minus 1 over A naught equals, let me put the actual number there. Be 0.400 molar. And then our K is 0.0480 over seconds times molarity times, and it says 15 minutes here, but it's in seconds, so we need to change that to seconds. So 15 minutes times 60 gives us 900 seconds, if I did my math right. All right, and from there you should be able to solve for concentration of A. Yes. Yes. All right, and then the last problem, and again, I'll just set this one up. I'm not going to actually do it. Says the initial concentration of NOCl described in its number 4. It's actually number 12 for us. In number 12 above is 0.4 molar. Yeah. The initial concentration is 0.4 molar. Calculate the half-life of this reaction. So remember, it was a second order. So second order half-life.
So when it's asking you for the, never mind.
So when we're doing where did I write the second order half-life? Oh, so second order half-life is basically going to be 1 over A naught over 2 minus 1 over A naught equals KT 1/2. All right, and you just solve for T 1/2. So basically, we would have 1 over 0.400 molar. Our rate constant for that one was what was the rate for number 12? Point.
The K?
Yeah, the K.
0.0487.
So you're just solving for T 1/2 in that one. Does that make sense? All right, then you go to your L2 column, and in this one you're going to just enter in what you see. So 1.5. Don't forget to put it into your scientific notation, or you could just go ahead and put in the numbers how they're supposed. Otherwise, it'll be -3. So it's going to be 0.0014 0.00127 0.00118 0.00103, and then the last one is to the -4, so it's 0.0009. All right. So when you get to this point, let me know. Yeah. So to do a batch edit, you're going to go ahead and go all the way up to the top and where your cursor is highlighting the L3. And so we want everything in this column to be Ln of the concentration. So I'm going to go Ln second, and I think L2 is the number 2 button. So you'll do Ln L2, and it'll put those numbers in for you. And then for L, you just move your cursor over to L4, make sure it's highlighting L4, and we're going to batch edit again. And so that one will be 1 divided by 1 divided by L2 again. And then you get that number of 666.6666666666666. All right, very evil number, but that's okay. All right. Oh, to do the other one?
I'm pretty sure I messed up on
No, you got it right.
Okay, it's supposed to be that 9 eV.
Yes.
Oh, okay, I didn't know.
So,
That looked weird.
so now you're going to come here, and you're going to go Ln second, L2. And it does your numbers there.
And then you do ln second to L4.
No, for this one, you're going to go 1 divided by, because it's 1 over, you're going to go 1 divided by L2 again. And then it gives you that. All right, so now that gives you your information. So after you've entered that in, now we can do our next step. Next step is going to be to calculate linear regression. And in order to do that, you need to go to Stat, Calc, and then you're going to select linreg. Now I don't know which operating system mine has, so this does it a little different for different ones. So if you go to Stat, move it over to Calc, and then it should be number 4 on the list, or if you just hit number 4, it may give you this little screen like that, or it may give you an edit screen. I don't know which one it's going to do. So if you get the one where it comes up to your regular screen and it says linreg ax plus b, you're going to do for 0 order, you're going to go second L1, comma, second L2, and then you hit enter. If you get the one where it tells you to edit, your first one's going to be L1, your second one's going to be L2. It just depends on how new or old your calculator is. If you know how to do this, great. But what I want you to record, or what I want you to write down on this, is you're going to have a column for slope. You're going to have a column for R2. And you're going to have a column for order. I want you to do it for all 3 orders. So our slope on this one is going to be our A, so our slope is negative 4 times 10 to the negative 8. Our R2 is, our R squared is 0.994. And then the order is, this one was the 0 order because it was just concentration. We're going to do it for first order, and we're going to do it for second order. All right, so now from here you just hit Stat, go back to Calc, select number 4, which is linear regression, and this time we're going to go L1, comma, and what column am I going to use for the second one? All right, so you'll use L1 and L3 this time. And so whenever it does it, it'll give you some different numbers. So our slope is going to be negative 3.41 times 10 to the negative 5. And look at our R squared on this one. It is 0.9998. All right, so that one is really close to 1 compared to the next one. And then we'll do it again. Stat, Calc, linreg, and then this time we're going to go L1, L4, and that one gives us, so 0.029 6. And then our r squared is 0.994. So which order is this reaction? Which one's the closest to 1? First order. So that's the one that we're going to select. Now, when it comes to writing your answer, you're basically going to say that you would say that is so k equals negative 3.41 times 10 to the negative 3. And that it is first order. Then you're going to write your rate equation. So rate equals k times N2O5 to the first. And then you could potentially solve for k if you wanted to using some of the information, or you already know that your k is the absolute value, so it's not a negative. K is the absolute value of the slope, so it's 3.41 times 10 to the negative 3. All right, so on your answers for these, I do want to see this table so that I can verify that you did all three. And then your final answer, when you select it, you're going to write this information, your K, what order it is, and then show me the rate law based off. To get it to do it? All right, so basically I select up there and I tell it to do, I would go, so for second order, it's going to be 1, this one would be 1 divided by, and it's going to be L2. And then that does a batch thing where it does it there. And then for L3, for first order, it's 1 over A. So you would go, I mean, not 1 over A, it'd be ln A. So that one you do ln second L2. And that just, that way you don't have to do each one manually. It does it all at one time. It just saves you some time. All right, so that is it. I want you to do 15 on your own. I'm going to go ahead and tell you for number 15, I'm going to tell you what answers you're looking for ultimately. So when you can plug it in. So for number 15, you should end up with a second order. You should end up with a K of 0.5475. And you can figure out the rate law based off of that. Yes. So it will